Am I audible? Let me know.
Yes, sir.
Okay, then the screen is visible. Let me know whether the screen is visible or
Yes.
not. हाँ माँ हाँ ठीक है, देखो मैं क्लास ले लूँ, बाद में बात करते हैं। हाँ लेके आओ कुछ भी, लेके आओ कुछ भी लेकर। Okay, class, the screen is visible. Let me know.
Yes, sir.
Okay, we will start. We have started bunkers and silos. Uh, we will see we have done in the previous class, and then we will move forward. The common names for bunkers and silos are beams. Bunkers and silos are used to store the material like the construction material or the coal, grain, or cement fly ash. So basically, it is a storage material. Okay, it is used to store the material. And the bunker, it could be of RCC and it could be of steel. In our syllabus, we have to deal with the design of RCC bunkers and silos. And this is the typical component of the bunkers and the silos. It has a vertical wall and it has hopper bottom. Okay, there are columns and there are also beams, but we are not concerned with the design of beam and column. We are only concerned with the design of vertical wall and the hopper bottom. And it is common in the bunkers and so in the silos. Okay, so bunkers are termed as small beams. Those are small in size, and the silos are termed as large beams. And bunkers, it could be of rectangular shape, it could be of square shape, and also you will also get the bunkers of circular shape. But silos, most oftenly, silos are of circular or cylindrical shape. Okay, and we have to distinguish between the bunkers and the silos. If you draw this line with respect to this angle, 90 plus phi divided by 2. What is phi? Phi is the angle of friction between the material stored and the concrete. If you draw the angle from this point, if that line touches the horizontal surface, then it is a bunker. If that line touches the opposite wall, then it is a silos. Okay, so silos are the deep bins and the bunkers are the small bins. Okay, and this is the hopper bottom, and hopper bottom, the hopper bottom is theta, which should be greater than phi. What is phi? The angle of friction between the material. Okay, the hopper bottom is provided with the opening so that the material can go out of bunkers or the silos. Okay, so we will first we will do the design of rectangular or square bunker. Then after that we will study the design of sur bunker. Okay, so in the design of rectangular or square bunker, you have to design the vertical wall and the hopper box. So the vertical wall is subjected to the pressure with respect to the material, that is lateral pressure of the material, and it is also having frictional force between the material and concrete surface. So there is a friction between the wall and the material. Okay. So since bunker is smaller in depth, bunker is smaller in depth, frictional forces can be neglected. Frictional forces can be ignored. So when you are dealing with the design of vertical wall, only little pressure should be considered. No frictional force should be considered in the bunkers because the depth of the bunker is smaller. Okay. So we have to design the two things, vertical wall and the hopper bottom. So in the previous class, we have seen the design of vertical wall. What should be there? So the lateral pressure exerted on the wall is given by the Science formula. Any question you have? Are you getting what I'm teaching? Hello, class. Hello, can you hear me?
Yes, sir, audible.
Okay, thank you.
Yes, sir.
So the lateral pressure exerted on the wall is given by Rankine's formula. So this is the Rankine's formula, gamma h cos beta, and this is what is given by the Rankine formula, where gamma is the unit weight of the material stored, h is the depth measured from the top of the stored material, beta is angle of surcharge, and phi is angle of repose. This is the angle of surcharge. So you provide more materials and it top ups like this. It comes in this shape, and whatever angle that material create with respect to the horizontal surface, that is beta. Okay, and this is the formula of pH. We need pH. P is inclined and we need pH. So pH equal to the cos beta. Okay, the maximum angle of surcharge is naturally equal to the angle of repose. So beta is equal to phi. So this is what we are getting discussed about this in the previous class. So pH, the horizontal pressure exerted on the wall is given by gamma h cos square beta. Okay, so this is the rectangle or square bunker, whatever. If the size are similar, then it will be called as square bunker. If the L and the B are different, then it will be called as rectangular bunker. So design is similar, okay? Okay, so we will start with the design of vertical wall. In the vertical wall design, you see, we'll get the bending moment with respect to the lateral pressure. So the corner bending moment is MA equal to MB equal to MC equal to MD equal to. So you see, I have defined the corners A, B, C, D. So you will get the bending moment at the corners, and also you will get the bending moment at midspan. And you have to calculate those bending moments. So bending moment at the corner is given by minus PH divided by 12 L square plus B square minus BL. If it is a square bunker, then the formula will be PH L square by 12. If it is square bunker. If it is a rectangular bunker, then you need to refer to this formula. Okay. Then we have bending moment on AB and CD. Bending moment, midspan bending moment, or you can say positive bending moment. So the corner bending moments are the negative bending moment, and the midspan bending moment is positive bending moment. Okay. So positive bending moment on AB and CD. Okay. On AB and CD means we are referring to the rectangular uh, bunker AB and CD. Okay. So the length of AB and CD is L. So that is why first we are referring to the positive bending moment on AB and CD, that is at the midspan. So it is given by PH. L is the span of AB and CD. Okay. Divided by 8 minus PH by 12 L square plus B square minus BL. So the bending moment, positive bending moment on AB and CD. Similarly, we need to find positive bending moment uh, on span AD and BC. On AD and BC. Okay. So the span of AD and BC is B. So PH B square divided by 8 minus the corner bending moment. Okay. PH divided by 12 L square plus B square minus BL. So you are getting bending moment. The bending moment means bending moment at the corner here. You are getting bending moment at the corner. So those bending moments are the negative bending moment, and you are also getting bending moment at the midspan of AB, of BC, of CD, and D. So those bending moments that are there on the midspan, those bending moments are positive bending moments. Okay. And the corner bending moments are the negative bending moments. Okay. So these are the formulas you need to, refer. Then you also have tension on the wall. Okay. For example, if this is,
हेलो।
yes,
सर एक डाउट था। सर जो मिड
हाँ
स्पैन
पूछिए।
बेंडिंग मोमेंट है, उसमें हम लोग जो
हम्म
कॉर्नर बेंडिंग मोमेंट माइनस कर रहे हैं सर, तो वन टाइम ही माइनस करेंगे। अगर हम लोग
हाँ,
एडी वॉल या
फॉर
बीसी वॉल देखेंगे तो उसमें दो कॉर्नर आ रहे।
फॉर एग्जाम्पल ये देखो, ये आपका बीम है, समझो फिक्स्ड बीम है, ठीक है। ये आपका फिक्स्ड बीम है। इसका बेंडिंग मोमेंट कैसा रहेगा?
कॉर्नर में सर हॉगिंग रहेगा, नेगेटिव, और मिड में
ऐसा रहेगा ना?
पॉजिटिव।
ऐसा रहेगा ना?
यस सर।
ठीक है। और ये आपका नेगेटिव है, कॉर्नर में नेगेटिव है। ये आपका नेट बेंडिंग मोमेंट कितना है पता है आपको? यहाँ से यहाँ तक कितना है पता है? WL² बाय 8। तो आपको नेगेटिव मोमेंट माइनस करना पड़ेगा ना नेट निकालने के लिए। पॉजिटिव बेंडिंग मोमेंट की
यस
बात कर
सर,
रहा हूँ मैं।
समझा।
ठीक है, तो ये
यस सर।
कितना हो जाएगा मालूम? PL² बाय 24 हो जाएगा। ठीक है, अगर आप स्क्वायर स्क्वायर बंकर से अगर आप डील कर रहे हो, तो ये आपका PL² बाय 24 ही हो जाएगा। ठीक है, you got this?
यस सर।
Okay.
यस सर।
So next we have direct tension. This is okay. This is the bunker that you have, whether square bunker, rectangular bunker, whatever it may be. See, the pressure is acting like this. Pressure from the material will be acting like, and this force I will name here A, B, C, D. So this force will create tension on AD and BC. Am I right? Am I right? Anyone can tell me? The force that is whatever the force drawn, that force will create tension on AD and BC. What will happen to AD and BC? It will be stretched. The length will be increased. Means it is subjected to tension. And because of this force, this pressure, which is in red color, because of this pressure, tension will be there on AB and DC. So the point is that all the walls of the bunkers are subjected to tensile force, are subjected to tension. So we also have to find the tensile force, and we also have to find what is the reinforcement with respect to the tensile force. Okay. So there is bending moment. You understood the corner bending is there, and the midspan bending moment is there. That is positive bending moment. Apart from bending moment, the bunkers, the walls of the bunkers are also subjected to tension. Okay. So the forces in the black color will tension on AD and BC. The forces in the red color that I have shown will have tension on AB and DC. So how to find that tension? If it is a rectangular, then we need to, see what is the tension in the long wall and what is the tension in the short wall. If it is square bunker, we don't have to worry because both the sides will be same. Okay. So if it is a rectangular, then direct tension on long wall. Direct tension on long wall. Okay. Direct tension on long wall equal to PHD divided by 2. So this is the tension on the long wall. Okay. And similarly, you can find tension on the short wall. on the short wall. Tension on the short wall will be PHL divided by 2. So in this way, you need to find the direct tension, and we will see how to find the AST, area of reinforcement, with respect to the bending moment, with respect to the direct tension in the problem. So this is about the vertical wall. Now we will see what is there in the hopper bottom, design of hopper bottom, design of hopper bottom. Hopper bottom is just like a sloping slab. It is just like a sloped slab. It is like this. So it is subjected to the weight, and because of this weight, there will be tension in the hopper bottom. So tension can be shown like this. Okay. And this angle is theta. The angle of hopper bottom is theta. So the hopper bottom is subjected to two forces. One is direct tension, and other is it is subjected to bending moment. Bending moment. Okay. So first we will see what is the direct tension in the hopper bottom. Direct tension in the hopper bottom. Direct tension in the bottom. Okay, so whatever W is given here in the diagram, it is the weight of the material that is stored plus weight of the hopper bottom. So this W is weight of the material, weight of the material that is stored plus self weight of hopper bottom. Self weight of hopper bottom. You see, if you resolve the T in the vertical direction, so this T cos theta will be equal to W if you apply summation of f of y equal to 0. So T is inclined with respect to, sorry, T sine theta. It's not T cos theta. T sine theta. T sine theta equal to W. So what we are doing, the T is inclined theta with respect to the horizontal. The vertical resolution of T is T sine theta, and that T sine theta will be equal to W. T sine theta. So in this way, you can find tension in the hopper bottom. T sine theta is equal to W. W is the weight of the material plus self weight of the hopper bottom. T equal to tension in the hopper bottom equal to W divided by sine theta. You can remember this formula or you can do this formula, whatever. You need to find the tension in the hopper bottom, and this is the formula. Okay, next we have how to find the bending moment in the hopper bottom. Okay, to find the bending moment in hopper bottom, we need to invoke the pressure, the normal pressure. Okay, so this is your hopper bottom, which is inclined theta, and this is the normal force. I will call normal force as Pn. Okay? And here the horizontal force is acting, horizontal pressure, that is Ph. Okay. and this will be, and the what force is acting, that is PV. Okay. Now what we are doing here, we are assuming a strip. We are assuming a strip like this. This is one. Okay. The inclined strip is one. And what will be the horizontal? And what will be the vertical? Can anyone tell me? This is theta. Vertical will be what, the horizontal? 1 cos theta. Am I right? And what will be the vertical? 1 sin theta. So here on the vertical, PH is acting. On this horizontal, PV is acting. And on this inclined, PN is acting. PN. Okay. If you take this vertical downward, it will be like this. And if you take this horizontal here, it will be like this. This is PH and this is PV. Okay. So you have to multiply with respect to the length, whatever length they have, Pn into 1. Okay. PH into 1 sin theta and PV into 1 cos theta. Okay. So what you are getting here, you see, this is your inclined Pn, vertical is PV cos theta. Pn into 1, you are multiplying the length, whatever length it's having, the length of the strip, you are multiplying to that. Okay. And this is theta. Okay. And here you have PH, PH into sine theta. Now what we have to do, this force and this force has to be resolved in this direction, in the normal direction. So when you do that, this is simple geometry. If you are confused, you have to invoke the resolution of the forces from the mechanics. From that we are getting this. Okay. So PV, what is PV? I will tell you what is PV. PV is gamma H cos theta. Sorry, PV is gamma H. Okay. So when you resolve in this direction, what is happening? You see, Pn, PV cos theta into cos theta. So Pn equal to PV cos square theta, because already it is having cos theta. When you resolve in this direction, again there will be cos theta. So it will be cos square theta plus PH is also resolved in this inclined direction, in the normal direction. Okay. So the angle will be sine 90 minus theta, and that will be equal to sine theta. Okay. So PH sine square theta. Okay. So this is what Pn formula we are getting. Pn equal to Pn equal to PV is gamma H. Okay. Gamma H cos square theta plus PH H sine square theta. Okay. And if you are considering the self weight, this is the formula that you are getting with respect to the pressure from the material. If you consider the self weight is acting vertically downward, that is W, and angle is theta. If you resolve the weight which is vertically downward, if you resolve that weight in the normal direction, it will be equal to Ws cos theta. Okay. If self weight is included, so the formula of the Pn Sulfate is added in the formula plus Ws cos theta. Okay. So this is the formula of the pressure on the sloping slab on the hopper bottom. Okay. So by this formula, you will be able to calculate the pressure on the hopper bottom. Okay. Okay. So I will find negative bending moment. Negative bending moment equal to Pn L square by 12. If it is a square, okay. If you are dealing with the square slab or rectangular slab for that matter, how to calculate this L, I will tell you in the problem. Okay. So negative bending moment, this is the formula. How to calculate Pn, I have given in the formula. Positive bending moment, equal to Pn L square divided by 24. So we have seen how to find the tension in the hopper bottom, and we have also seen how to find, the bending moment in the hopper bottom. Now we can see the problem and we can solve the problem. So these are the some of the derivation of the formula that we have to use in the problem. Up to this is clear? Any question, class? Do you have any question? Hello. Okay, once we see the problem, things will be very, very clear to you. Okay, how to use those formulas. Okay, we'll see this problem. Design a square bunker. Design a square. We only have 10 minutes. Okay, so whatever things that will be covered in 10 minutes, that is okay for today's class, and we will continue tomorrow. Design a square bunker. Weight of the coal is given. Okay, weight of the coal. Weight of the coal is given in the problem, which is equal to 350 kilonewton. Then density, weight density of the material is given, that is 7850 Newton per meter cube. Phi is given, that is angle of repose, 30 degree, and M20 and Fe415 steel has to be used in the design of bunker. Okay, so phi will be equal to beta in case of, if you have surcharge. Okay, so first we will see the dimension of the bunker. Dimension of the bunker. It is like this. This is the vertical wall. Then you have surcharge. Okay, then you have surcharge. Then there is a hopper bottom like this. Okay, sorry, hopper bottom is provided with the opening. So there is some opening in the hopper bottom like this. It is provided with this opening. I will tell you the size of this opening. So I will call this as H1, this as H2, and this as H3. Okay, and this is my 5, which is also equal to beta. Okay, so the size of the bunker is not given. Okay, we'll assume the size of the bunker. They have asked us to design the square bunker. So we'll assume 3 meter by 3 meter square bunker. Square bunker in plan. So if you see from the top, the size of the bunker is 3 meter by 3 meter. Okay. And this angle that they have given is 30 degrees. Can you find H1? How to find H1, I will tell you. See, this is what is given. This is the surcharge. The above part is surcharge. And the size of the bunker is 3 meter by 3 meter. Okay. This angle is given 30 degrees. Can you find H1? Class, can you find H1? From here to here, it is 1.5 meter. Okay. Can you find this height? Class, am I audible to you? Hello. Simple. Can you find this height?
Cos theta, sir.
Yes.
Cos theta. What about
Tan
tan
theta,
theta?
sir. Opposite divided by adjacent.
Uh, Tan theta equal
Yes, yes.
tan theta. So what H1 you are getting? H1 equal to, see, tan theta,
1.5
tan
tan theta.
30 equal to H1 divided by adjacent. What is adjacent? 1.5. Am I right? Adjacent of the triangle is 1.5. Am I right?
Yes, sir.
Am I right about this? Okay. So what is H1? H1 equal to 1.5 into
1.5 tan 30.
tan theta, tan 30. So what you're getting? H1 equal to 0.87. Am I right? Am I right about this?
Yes, sir.
Okay. So you got the H1. Now first you find the volume of surcharge. It is just like a conical shape. So you have this rectangle. Rectangle is, having like this. It is like this, okay? If you, I can show in the 3D if you want. It is like this. This is your surcharge, like this, okay? Conical shape, okay? So first we will find the volume of surcharge. So volume of surcharge is denoted by V1. Volume of this, whatever this the portion is there, it is denoted as cylindrical portion. No, not cylindrical portion. Okay, V2. Whatever this portion is there, the volume is denoted by V2, and the volume of the hopper bottom is denoted by V3. So first we will find V1. So this is V1. Okay, this is V1. First we will find V1 because we know the height H1, and we also know the base dimension. It is 3 meter by 3 meter. Okay, so V1 is denoted by V1 is calculated as V1 equal to 1 by 3, the base dimension 3 into 3, and the height H1 is 0.87. So this is your V1, okay? V1 equal to, can anyone tell me? It equal to 2.61 meter cube. Okay, you got. And you know how to find the volume of the bunker. What they have given, they have the weight of the coal, and they have given the density of the coal. You know the difference between weight. See, weight equal to density into volume. You know this formula? Everyone, please. Let me know, you know this formula? Weight equal density into volume.
Yes, sir.
So can we find the volume of the bunker, entire bunker? Because weight is given, whatever material we need to store in the bunker, the weight of that material is given to you, right? And density is also given. Can you find the volume of the bunker? Volume of bunker equal to weight divided by density. Okay. So what is weight? Weight is 350 kilonewton. We can convert that into Newton. Okay. 350 into 10 to the power 3. And what is gamma? Gamma is given to 7850. Okay, so the weight, so the volume of bunker that you are getting is 44.60 meter cube. This is the entire volume of bunker that you are getting, and from it you have calculated V1. V equal to, this is V, okay? V equal to V1 plus V2 plus V3. What you have calculated is volume of surcharge, volume of the upper part of the bunker. You have now you have to calculate V2, the middle portion, the volume middle portion, and V3, that is volume of upper bottom. But already I have gotten the entire volume of the car, that is 44.60 meter cube. Okay. Okay. So we have found V1. Not one. No. Now what we will do? We will find the V3 before finding V2. To find V3, we should know the angle. We only have less than 1 minute. Tomorrow we'll continue if it gets stopped.